Thank you so much for the invitation for this webinar of today. I will be speaking about physical and mechanical properties of pyrolyzed pellets. My university is Bialystok University of Technology. And for those who don't know about it yet, I want to shortly say it's located in eastern Poland, so-called lungs of Poland, because we have a lot of forests and a very well-developed agricultural zone in this part. So that's why we're interested so much in pellets, and I divided my presentation of today into three main parts, where I want to speak about pelletization and pellets. Then I want to show you a brief literature review about how pellets are transformed to biochar, and I will support it with my own studies about physical and mechanical properties of pyrolyzed pellets. So firstly, what are pellets? Because we are thinking about pellets, so they are some kind of granules, right? But actually, they are very well described, normalized cylinders of a diameter from 6 to 8 millimeters and a specific length from 8.15 to 40 millimeters. And pellets are produced in the so-called pelletization process, which is pressure agglomeration of previously comminuted materials. And this process can take part in two, or let's say three different ways, main ways. So in industrial scale, we are using pelletizers, so-called pellet mills, granulators, and as a result of external and internal forces in the working system of such a device, marked at this slide in figure 1AB, the given material is compact to a specific constant geometric form, and this compaction can take place in a granulator with a fixed flat matrix or a ring matrix. But in literature, also a lot of pellets are prepared in a single press pellet device, and I will come back to this kind of devices a bit later. They allow us to steer the process conditions very precisely to just control how the pellets are made in specific conditions. And these conditions that affect pelletization, they can be divided in a couple of groups. First of all, chemical and biological material characteristics, perhaps the starch content, lignin content. The design factors, such as which kind of pellet mill we are using, what kind of matrix is it, what are the hole diameters. Process factors, as we can describe as the feeding rate, the rotational speed, and so on. And very important physical material characteristics. And the most important here, moisture content, which has to be optimized for any kind of feedstock anytime we run the pelletization process at a certain device. So as I told you before, pellets are very well specified and they are normalized. And in order to get a certain quality, reach a certain quality threshold, we need to keep some standards in very high. Let's say perhaps for pellets, we need to measure the diameter, length, moisture content, ash content, and so on. And these standards are applied mostly for woody pellets. So if a woody pellet has a certain certificate of, let's say, EN plus A1, but there are also other standards, we are sure that the pellet is a very high quality feedstock. However, also pellets are not only made from woody biomass, but from other biomass sources such as agriculture waste, food waste, and so on. So we don't have standards for this feedstock that's strict. However, we are always pushing to have our pellets as good as woody pellets. So why are these feedstock gaining so much popularity in last days? They're actually affordable, they're easy to store, easy to transport, they're very convenient. In combustion processes, they allow us to reduce greenhouse gas emissions in compared to fossil fuels. And one of the main factors is the waste management possibility, because pellets are products made from waste. If it goes about woody pellets, they're mainly made from some low-quality wood, tannings, mill residues. We don't produce pellets out of wood that can be used in construction or furniture production. However, an alternative to produce pellets is the food sector, actually food waste. And what I'm interested in is the food production waste, which covers the agricultural production and harvest, and also food processing, as these wastes are hard to dispose, they're problematic, but they still remain as a source of carbon. So we are all the time looking for a way to make the food production more sustainable and more circular. And I made a short literature scan about how pellets are transformed to biochar. I was digging in Web of Science and Google Scholar and checking the keywords such as pyrolysis of pellets, biochar from pellets, and pellets biochar. And I detected currently 22 papers that are detailing slow pyrolysis of pellets, from which 19 of them were studies based on a fixed bed reactor, and just three of them on a continuous fed reactor. And what I need to highlight right now, that pellets actually, they're meant to be used in continuous fed reactors, because we need to have a certain energy input to produce the pellets. So in order to give justice and make the process more efficient, it's more likely to use continuous fed reactor, I believe. But sticking to the pellets, so industrial pellets that were made in a pelletizer covered 67% of the literature scan, and single press made pellets 29%, and for 4% we didn't have any data. So on the left-hand side, as shown on the graph, the majority of pellets used to produce biochar were wood-based, covered 21%, and there it was followed by such a feedstock as corn straw and a smaller share of other materials that had been used to produce pellets and then transformed to biochar. So as I shown a table about the pellet properties on the very beginning of this presentation, I copied some of these requirements also to this slide. And what I need to say from the literature scan, out of 29 feedstocks that were described in 22 papers, just 18 of them had the ash content described, just 10 of them had the length, and just for 15 cases we knew the diameter. So these are very critical parameters to understand what kind of feedstock we are using for pyrolysis. Only one study had the mechanical durability, which is also interesting, because also it provides us transportation requirements. So it gives us an information how the pellet will be transported automatically or in trucks, how it will be packed, how it will be performed further on. And as the wood pellets had the biggest share in the literature data, I summarized them in table 1. And as you see by the gray lines, I marked what is missing in this for estimating how the pellet properties affect the biochar. So the only full description was for the temperature that the pyrolysis is performed and also the biochar yield that we got. And I tried to estimate if there is any connection between woody pellets and the biochar yield. However, even dividing them into industrial and, let's say, single press pellets, I couldn't meet any estimations here that would be satisfactory. So from the other side, I started to look on pellets, how the feedstock and how the size of pellets, or let's say that they were coal pellets, were affecting the biochar yield. So also here in 400, 450 degrees or in 500 degrees, I didn't reach any solid conclusion. However, it was noted that pellets, if they are processed in comparison to powder biomass of the same time, they can provide us to reach higher biochar yields. However, as we tested later in our own studies, not for all cases this is working that way. One paper showed the durability of pellets, how it's changing during pyrolysis. So in comparison to the raw biomass, we see that in, let's say, low temperatures of 400 degrees, the durability drops significantly. But however, increasing the temperature provides us to receive pellets from a higher durability, and it was also in line with the data that we obtained during our studies, and I will show it on the end of this presentation. So this all inspired me to create some pellets made of 4 different feedstocks, which are waste from agriculture and food production. So buckwheat husk was used, hemp hull, giant miscanthus stalks, and hazelnut shells. And additionally, for some cases, binders also were used for pelletization in the form of potato pulp, which is the residue from the starch, potato starch production, or spent coffee grounds also were used as a binder. And in this place, I would wish to thank you for a cafeteria in Bialystok, White Bear Coffee, to collect through whole of the weekend these spent coffee grounds to make this research happen. So pelletization took place in a fixed matrix rotating roll pelletizer, which is a part of a pellet production line at the Bialystok University of Technology and Pyrolysis. Together with Christian, we performed at the UK Biochar Research Centre at the University of Edinburgh. We ran the pyrolysis process at 2 different temperatures of 550 and 700 degrees. So we wished to compare also how pellets behave, well, maybe not behave, maybe how the biochar properties are after pyrolysis in comparison to raw biochar, the plants in comparison to pellet. And what we found out that pelletization allows us to improve the bulk density of the final product even up to 4 times, perhaps for buckwheat husks at 550 degrees. The bulk density of pellets was over 4 times higher than for the raw biochar that was pyrolyzed in exactly the same conditions. So focusing on pellets, we found out that in both temperature scenarios, we have a direct effect of the pellet bulk density on the biochar bulk density. So the higher the bulk density of pellets that were subjected to pyrolysis, the higher bulk density of the biochar obtained. So here the correlations were a bit stronger for 550 degrees than 700 degrees. However, still we can say that the correlation is very strong for both scenarios. We also compared the particle density of pellets to the particle density of biochar, also with a strong fit. However, the particle density might affect also the bulk density of pellets. However, it might affect positively and negatively because it depends on the type of pellets that we have. For longer pellets, actually, we can have a quite dense particle. However, the bulk density, because of creating open spaces in a certain volume, can be pretty low. That's why perhaps most of pellets are kept at shorter length than perhaps 14 millimeters as the norm says. So another outcome, one of I find most interesting out of our data, is that by measuring the particle density of pellets before and after pyrolysis, we can estimate the biochar bulk density. So for 2 temperature scenarios, we received a very strong fit for this data, and it can be a very important outcome for perhaps scientists or researchers or stakeholders that have a limited amount of sample, perhaps using smaller devices that you cannot produce as much sample to measure properly the bulk density. By running these calculations, you can estimate the bulk density of the resulting biochar, which is a critical factor to perform or calculate transportation or other handling costs. Regarding the mechanical properties of pellets, we checked the stress upbreak, and indeed for some pellets, our data is in common with the ones published in the literature. So the higher the temperature was, the higher the mechanical strength of pellets was. However, for testing so many variables of pellets, we can also summarize that this property is not always same for certain feedstock. So perhaps the buckwheat husks and the hazelnut shells, indeed, the mechanical strength was higher at higher temperatures. However, for hemp hair or jank miscant styles, which are a bit containing fibers, the mechanical strength was kept on the same level. And to shortly summarize the presentations, I want to highlight that pellets used as feedstock for pyrolysis require additive characterizations. As you saw from the literature study, it would be very beneficial to have more data to understand what is the behavior of pellets and what can we expect, how can we expect the biochar properties to be. The bulk density and the particle density of pyrolyzed pellets is a result of the biomass pellet density, as shown on the correlations. It is possible to estimate the bulk density of biochar basing on the particle density of biomass pellets and pyrolyzed pellets. And it's uncertain what will be the mechanical strength of pellets, uncertain yet, because some of the feedstocks, indeed, it's correlation with the temperature. However, it does not apply for all of these samples that we have investigated. So that's for today. Thank you very much for having this chance to show my research, and I'm willing to hear some questions, comments. So thank you so much.
Thank you very much, Magda. The floor is open to questions now. So if you have any, please write them into the chat. So the first question, so now we see you as well, Magda.
I didn't want to take the risk.
Yeah, now it's working. So Akshay Maktoum was asking, is there a significant difference between wood pellets and agri pellets in applications for heating or pyrolysis? Or do you have a preference between woody pellets and agri pellets?
Well, actually, I would prefer to use the agricultural and food waste pellets. Why? Because wood is still a good, let's say, wood waste pellets are still a good feedstock for combustion. So I would not want to be here on the line that we are using for pyrolysis. Some materials that are good in combustion, since they are still needed, and some of agricultural residues are not that significant in combustion. And I have an extra slide actually right now, so I can answer with this slide. So this is the last one that I wanted to show to you. So here we have a comparison of some pellets that were combusted in a fixed bed combustor with a rotary grate. It was my previous interest, and that's why the biochar came to my mind. And what we had here, some feedstocks, indeed, they were pretty fine in combustion, that the emission rates were kept on the eco-design, in the eco-design frame range. But some of them, perhaps like buckwheat husks, even though the carbon content is comparable to woody biomass, still the CO, carbon monoxide emission was extremely high for this feedstock. So I would prefer to use the agriculture waste materials rather than woody pellets for producing biochar, if it goes about my opinion.
Yes, a nice backup slide. So George was asking, how are LCAs affected given the energy required to pelletize material? So how would that affect the carbon emissions or the overall environmental impacts?
Do you mean how the energy of pelletization, right?
Yes.
So you made some calculations. So I think here, if goes about pelletization, which is a process that requires a lot of energy, I think the most important thing is that we still have the waste disposal. So if we can transfer the waste into pellets and use them in a certain application, it's better than combusted in a raw form or let them be left on the landfill. And if it goes about the energy consumption of pelletization, it's a very energy consuming process, first of all. However, there are ways of limiting this energy consumption by perhaps adding some binders to the feedstock, like the potato pulp I used or the coffee grounds. But from our calculations that we have on now, it's not in the terms of production of biochar, pelletization doesn't play the key role in energy consumption.
Okay, yeah. And from my side, one question, because you worked with binders as well. So coffee, spent coffee ground and potato pulp. So which one is easier to work with in the pelletization, or it?
I'm completely fan of potato pulp. So.
Oh, okay. Okay, that's a quick answer. So if there are any more questions, please write them now. Maybe my follow-up question for future papers. Have you tried to pelletize the biochar as well?
Yes, I tried, but this is a tricky problem.
Okay, so it's not
so I cannot share any results yet, but it's in progress. I think that first, as I shown you, the single press pellet device, it's the way to go for the very beginning to optimize the process, because running a pellet mill might be not that beneficial right now.
Okay. You also got another question in the chat, which is, have you looked at manure digestate pelletization? So not a food waste, but an animal waste.
I did not check this. However, as far as I heard on conferences, the manure is a very nice feedstock to produce biochar. Just the problem is that the moisture content is very high. Actually, I now remember that yes, I was working on manure, but not from digest. Just it was collected from a barn, and we need, in order to produce pellets, we had to dry it on air, and the process is, let's say, not that comfortable to run when you add moisture. Okay.
I can imagine the smell of it.